E antes de fazermos então a pausa para almoço, e porque uma das expressões mais utilizadas aqui, o que é que vem a seguir? What next? Nós achamos que este iPad, os telemóveis que aí tem, é o último grito da tecnologia. Conseguimos fazer tudo, encomendar comida, ir ao banco, até encontrar com quem vamos passar o resto da nossa vida, por exemplo. Mas não, o convidado que vem a seguir vai explicar que isso já era, para onde é que vamos agora, ou seja, esta nova era da economia digital móvel, o que é? Qual é a cloud que vamos precisar? Como é que vamos comunicar? Que sensores? Se isto já está ou não obsoleto? Shamik, Mishra, welcome. I was saying that probably what I have in my hand is obsolete in a few.
I don't think so. Not
almost?
at all.
No,
not now.
No, it's your stage.
That's the slide
I'm giving
changer.
to you. Thank you.
I'll wait for the slides to come up. Okay, thank you. Okay. Yeah. Okay. Hello, everybody. Good afternoon. Thank you for being here. My name is Shamik Mishra. I am the Global Chief Architect for the telecommunications business of ALTRAN. And I've been listening to some of the presentations for the past hour or so, and a lot of the things that I would like to talk about today is already covered. So maybe we'll just go through some of the key things that we learned in edge computing today. What I'll be talking today is primarily to build a new kind of mobile internet economy, which we are seeing is growing rapidly across the industry today, across the world, actually, and share with you some of the insights that we learned from such engagements globally. So let's look at some of the key challenges today in the industry today. So the communication networks are being more and more stretched to the limits because of the large amount of data and the demands on connectivity. And this includes the fact that the networks need to be more reliable because more and more devices are getting connected to it. There is a demand for speed. There's a demand for the quality of experience, which perhaps if you look back 10 years ago, the quality of experience on internet, on the phones, and the quality of experience today is significantly different. And this is not going to stop, right? There's more and more devices coming in, more and more new applications coming in. It's bound to change the way the quality of experience will drive internet. So that's another demand on the telecom networks. And of course, perhaps the biggest challenge for telecom networks today is in order to meet the first three criteria, the telecom networks has to invest a lot. And then how do they actually get back the money that they invest in getting better speed, providing better reliability, and then, of course, ending up with a quality of experience. So where is the economy heading towards? I mean, how does an operator, how does the operator actually end up getting money, making money out of a mobile internet? So there is a possibility today in terms of how we do that, and perhaps the change in the network connectivity towards 5G and edge computing could be an answer to that. So let's look at some of the key ideas on edge computing today. One of the most important elements of network communication today is latency. So previously it took seconds to reach from one location to another. The packet travels from one place to another. It takes seconds, and it cannot go faster than the speed of light. But then there are new applications coming up which demands lower latency. For example, the augmented realities and the virtual reality headsets that we wear, they require tens of milliseconds in order to be effective. Autonomous cars, a gentleman talked about that earlier, it definitely needs less than 10 milliseconds. You cannot possibly have an autonomous car which reacts in seconds, right? And then, of course, there is industrial equipment which perhaps even need to work in microseconds. Now, these applications, are they really a kind of model that would be implemented by telecom players? Previously, no, because the latency demands are too less. But with 5G and with the possibility of a new model like edge computing, where you can actually compute closer to the network or closer to the user, then you perhaps can solve this problem to a certain extent. So there are many other use cases, and I will go through that in a moment, but let's understand what exactly is edge computing. I mean, we have heard about that a lot. Let's have a very 101, edge computing 101 right now. So typically, we have a mobile phone that's in our pockets, and then there is an application which is running. Well, this opened up, I don't know. Can you hear me still? Yeah, okay, fantastic. So there is a client which is in your mobile phone, which sort of runs a client application, and then there is a service which is hosted in the cloud, right? Who builds this service? Who builds the service that is hosted in the cloud? It's built by an application developer, an average application developer, maybe from a startup who builds this application. These application developer reaches out to the clients or the different consumers through app stores, right? You go to an app store, you download an application. That's how a consumer gets access to an application. And the developer hosts the service in the cloud. I mean, that's pretty much how it is, right? And then the client and the service sort of talks to each other. I mean, this is a fantastic model. This is how the internet is consumed today. And if you look back 20 years ago, or maybe 15 years ago, or somewhere around that time, before the advent of mobile applications, we really struggled to consume internet on our phone, right? We perhaps used it for maybe mail or something, but it was very difficult to consume anything on the mobile phone for internet purposes. But that all changed when iPhone came up with the applications, a kind of an app ecosystem which sort of enabled this. And this has now taken up the most of the modern economy today. Now, this has a problem. This has higher latency. So the applications that I talked about, autonomous cars, virtual reality, most probably cannot take use of this because the cloud is way too far. I mean, you possibly cannot have a cloud in Seattle, and you're sitting here in Lisbon, you're trying to do something, it takes all the way, it will not go beyond the speed of light, it will take seconds to reach a service running somewhere far away. So things have started to change in the sense that the access latency is coming down faster because of 5G. There is a more new kind of virtualization technologies that the operators have access to. There is a concept which I'll be talking about today, edge compute, where you can set this up in localized data centers very close to the access points. And then the application developer will have to get access to this, right? And if they can, then this application can actually move much closer to the action. And once it goes closer to the action, the distance that needs to be traveled by the client is reduced significantly. And therefore, you can save money by not having to send the data all the way to the cloud. And the new kind of applications can be developed for different kinds of new devices. Now, this is all good in paper, So basically having small clouds everywhere is a very good idea, but is it really impossible to implement such a model? So let's see whether we can do that. So again, going back to the same model, you had a client, you had a service in the cloud. This network between the client and the cloud is all owned by network operators, telecom operators. Now, all that we are trying to do here is to create small clouds in between. So you have a large cloud, you have the device, and you create smaller clouds in between, right? So if you can create smaller clouds in between, now the autonomous cars don't have to go all the way to the cloud, but they can communicate to the local data center or local clouds. The drones, the manufacturing companies, the AR glasses can suddenly use this kind of a model to improve their latency and performance. So edge computing is nothing but actually creating small clouds all the way from the device to the public cloud, right? So creating this small cloud is perhaps best done by the telecom operators today. The reason why we are saying this is that they own the network anyway. So if they can collaborate on networking, like roaming, they can as well collaborate on compute. And together, they can create this new kind of cloud economy, which might change the way we are looking at internet today. The most important element here, and we shouldn't forget about this, is the application developer. The application developer is critical, because the application developer develops the application. The application developer is used to large public clouds, which is naturally the case. And the application developer can easily onboard applications on public cloud. You go to any public cloud today, it takes 3 to 5 minutes to run any application on a public cloud. The network operators, on the other hand, have a complex piece of puzzle to solve. They are notoriously slow, if I may say that, and they have a complex networking problem to solve. So naturally, they need to be a little more agile if they have to get these application developers to build applications meant for edge compute. And what are those applications? A very easy example is video streaming. I mean, video streaming is completely latency dependent. I mean, if there is high latency, the quality of video will be definitely impacted. So having the videos cached at local data centers in the edge of the network might make a very big difference to the quality of experience for the users. Augmented reality and virtual reality has been one of the most talked about use case in edge compute because of the fact that it needs very low latency. And I'll give an example of how this is changing. You've seen the augmented reality glass the kid is wearing here, right? It's a huge glass. It's heavy, it's large. It costs maybe around $4,000. You cannot really use it beyond a certain point, maybe 5 minutes, maybe 10 minutes. Beyond the point, it's really unusable. And also the cost is prohibitive, around $4,000, $5,000. It's pretty much prohibitive, right? But what drives the cost and the size of this AR glass? It is driven by the fact that you have virtually a computer running there. You have a GPU, you have a processor, you have software, you have connectivity pieces, you have everything running there. So therefore, it's a computer, and therefore, it costs more, and therefore, it's large. Now, if you can move all of that to a nearby data center and provide a strong connectivity between the glass and the edge, then you are actually able to bring down the cost of the glasses significantly. The glass may even look like this, right? The glass may come down, maybe hundreds of dollars rather than thousands of dollars, and the operators also start to get a model of revenues, right? Because if they can start hosting applications meant for AR in their edge compute, in their localized data centers, then this makes a hell lot of difference to the overall market for the operators. And also the device makers will be very happy because the fact that the glasses will become as cheap as a mobile phone, then it makes sense, right? For them, they will have a larger volume in terms of sales. Well, the last presentation was all about this, industrial manufacturing, which is all about a huge amount of data getting generated from large amount of sensors. Internet, as you know, works like a post office, right? If I want to send you a letter, I will be paying for the data. I put a stamp on the envelope, and I send it to you. So I pay for any data that gets transferred. Internet works exactly like that. So whoever sends the data pays for the data. Now, if this data has to go all the way to maybe in a cloud hosted somewhere miles away, then more the distance it travels, the more you pay for it. It's like post office, right? Like postman. So in an edge compute, if you have computing capabilities very close to where you are, then most likely you don't have to send those terabytes and then exabytes and petabytes of data to the cloud, and that's a huge savings in terms of simple internet costs. It's as simple as that. Yes, AI and other things will make things better, but it's the most important driver here is cost. You save cost by not having to send the data all the way to the public cloud. One of the key use cases which we are seeing, at least in North America, is about connected stadiums, a fan experience. It's hundreds and thousands of fans in a stadium. They're all utilizing bandwidth to communicate, to take videos, upload videos, and most probably even communicating with each other while sitting in the stadium. One great example is that you're at one corner of the stadium, you want to have an alternative view of what's going on in the other end of the stadium. You may want to use an application which takes a view from a 360-degree camera and gives different possibilities or different views for the spectator. It's not possible with like hundreds and thousands of spectators there to do this on a cloud. It has to be done on the edge. At least a compute has to be there in the stadium where you can process all of that data. Drones, we spoke about that in the last presentation as well. We are seeing more and more interesting use cases coming out of drones, particularly autonomous drones. For example, surveying, fixing electrical faults in large, highways, in oil and gas, in several other areas, in logistics, in delivery models. For example, you deliver a package from one location to another. Drones are becoming more and more pervasive. And these drones need to be fairly autonomous. And now you can't possibly run all the algorithms in the drone itself. So having a connectivity to a localized data center where you run these autonomous algorithms makes a hell lot of difference. Well, autonomous vehicles, I would not talk too much about it, but we all know autonomous vehicles create a huge amount of data from its lidars and radars and all the sensors around it, and it needs to be processed somewhere. One option is to process that data inside the car. Most probably that's the best way to do it. The other option is that maybe there could be use cases where you want to do accident avoidance or traffic monitoring. Those can be best done on the edge, on somewhere nearby, instead of in the car. Now, with 5G connectivity, that could be done really fast. The edge is just sitting very near to the car anyway, so it's like as good as running the algorithm in the car itself. Just that it's powered by a stronger connectivity like 5G. So if you look at all of these things, there are three main drivers that is proving to be important from edge computing perspective. One is the revenue stream. New applications, new devices, new kind of models are being introduced in this new internet of, not things, but internet of different kinds of use cases. There is a cost reduction that I talked about. You don't have to send exabytes of data, perhaps, to the cloud anymore. You can process it locally. That makes a massive difference to the cost. There could be other use cases, like productivity tools. Operational efficiencies can be improved by running things locally. A smart parking application, if you want to run it inside the parking itself in a localized edge compute rather than running somewhere far away, is just simply some simple common sense. It makes sense to do that there because you save on data, you can localize, you can kind of provide services very close to the user. You don't have to send the data somewhere centrally. So even though it is not latency sensitive, the parking is definitely not latency sensitive, but still it makes sense to do it locally. Now, if you look at the edge computing stakeholders, there are many stakeholders. We talked about the application developers. We talked about the fact that the device makers are important in edge compute because the device makers are going to drive how edge compute is built. The enterprises, why would they be interested in edge? There could be many use cases apart from just the ones that I talked about. SD-WAN is another example of enterprise-based edge computing. Enterprises can actually save a lot of money by virtualizing and moving towards an universal CPE kind of a model rather than trying to have specialized hardware for everything. And it makes big sense to run small data centers in enterprises. And then the operators. The key challenge here, that's the last part of my talk, is about how the operators make money out of this. This is all good, but how do operators make money out of this? Because when we are talking about an economy, it has to have a driver. And that's what we'll explore in the next couple of minutes. So let's look at the application ecosystem that we all talked about, right? So there are two elements to this, right? There is one element is about high speed and low latency. That's what we have been talking about. The other element is about interactivity and autonomy. The drones, the cars, they're more and more autonomous. And then there's a need for higher speed and latency. So there are basically two dimensions in edge compute. Now, if we go back in history, we can see that the internet size, the basic web browsing, was perhaps the least interactive, least autonomous, and it perhaps didn't need too much of speed, right? And even a bit of latency was okay. From there, we moved on to web applications, which became a little more interactive. Like you order a pizza, a little more interactive. You order a car, a little more interactive maybe, but it's still not very latency sensitive. Then comes videos, which is more dependent on lower latencies, more dependent on higher speed, but still not interactive. You don't interact with the video that much, at least not now. Then online retails, they are a little more on the autonomous side because you run a lot of machine learning algorithms there. But then the bunch of use cases on the right-hand side, autonomous vehicles, digital twins, drones, smart industry. These are the ones which are extremely autonomous or extremely interactive, and they demand low latency and high speed. So this is the kind of the spread of the application if you look in the 2 dimensions. Now, the first set of applications we can run on a PC, right? We are doing that for the past 4 decades. Then the next set of applications we are running on a mobile phone, most probably smartphones that we have today. And then this set of use cases are actually run on a new kind of devices, like next generation IoT devices. The one on the top, if you look, these are heavily dependent on artificial intelligence, on what kind of cognitive and intelligent software that runs on the devices or on the edge. So what edge computing actually encompasses is this. So this is the place where the edge computing matters, and this is what we call edge native. And if you look carefully, edge computing is a convergence of 3 distinct technologies. These technologies grew by itself. Next generation devices did not care about 5G connectivity. The artificial intelligence didn't know what edge compute would even exist when it started, right? It started a long time back. And the fact that the low latency connectivity is very, very recent. From 4G onwards, we have started to see low latency connectivity. So 3 different technologies, connectivity, AI, and next-gen and new kind of devices, they're all converging together, and that's perhaps where the edge-native applications resides today. And if you look at the business model that you see today is perhaps the right business model from an edge compute perspective. Developers having a B2B relationship with the operator who hosts the edge compute, right? The rest of the thing remains the same. This is exactly how the cloud works. Instead of the operator, there is a cloud there. So that's the business model that exists today. But the edge computing cannot be as scalable as a cloud because of the fact that each operator might have to do their own thing. So there must be some alternate way of implementing this business model. And the one model is what is known as the aggregator model, where the aggregator interfaces with the application developer, and then the operators are sort of interacting with the aggregator as a B2B model. Now, this is good, but the application developers are primarily stuck with the aggregator, and the aggregator kind of is a broker between the operators. But this can scale. This can scale because the aggregator takes care of the scale. More and more operators can actually connect to an aggregator, and the aggregator takes care of everything. But what we are trying to figure out maybe in the next couple of years, you would be hearing more about this, is that can the operators sort of collaborate with each other and federate themselves? They have done it with roaming. If they can do that with computing, then most likely there would be 2 different models for the operator in edge computing economy. They can have a B2B interfaces with the application providers, and they can have a revenue share between each other. That way, an application developer gets larger reach because each application developer can go across the geographies, and at the same time, the operators can talk to each other, and they can make some kind of revenue out of it. So this federation model is perhaps the right way forward. And I've been speaking on this for the last couple of years now, that how the operators need to kind of come together if they have to make this economy work, this edge computing economy work. I'll skip this piece. I'll come to the last part of my slide. So just to take a key takeaways as part of this presentation. So edge computing is perhaps the most important element in the new economy because it is a cloud which is distributed. Think of edge compute as not just as a NFV or a virtualization data center for an operator. It's small little clouds spread all over the world. Now that way, as an application developer, it becomes very easy for me to reach out to millions of devices. The telecom operator is perhaps the most suited to build this edge cloud, this new internet, because they own the network. They own the locations. They own the real estate where they can set up these small little clouds. So they are perhaps the best suited to do that. But like every internet economy, no operator can do it alone. They need to perhaps take along them other operators together. They need to collaborate. They need to federate. They need to bring enterprises and device makers into the picture and sort of build an ecosystem around it. Internet didn't get built in a year. Internet didn't get built just because somebody built a server. It is because there were devices, there were application developers, there were users. All the stakeholders provided input which built an internet economy. Similarly, the edge economy isn't going to be any different from that. It also needs to have a similar milestone. And then, of course, there are different kinds of, as I mentioned, edge computing is an amalgamation of 3 distinct technologies. So focusing on those technologies will bring out more and more applications that will suit the edge economy. That's it. Thank you very much. Pleasure to be here.